Thank you. Good morning, everybody, and welcome back to the AMSAT 2025 Colloquium. A few notices from our esteemed treasurer that at the gala dinner last night we had a small auction which wasn't planned, but some of our friends brought some, as we call it, we brought some swag to sell, basically. And we made £294. That was very, very pleasing. For those who were there and haven't paid, Kieran, you can do it. You can either find him, because he's going to be around till about lunchtime, so you can actually give him pound notes, or you can go onto the shop and make a donation through the shop, which is probably the easiest way. If anybody's got, if while Kieran's here, if anybody's got any membership queries, please go and find him. He'll probably be down in the special interest group room. Barry's going to take over as chairman now to do this session. Thank you.
So it's good to see everybody, and I think a few survivors from the dinner last night, which is good. The first presentation we've got this morning is a video recording from Michelle Thompson talking about microwave satellite ground station design. So, can we roll the tape, please?
Hello, everybody. My name is Michelle Thompson, and I'm the CEO of Open Research Institute. We are a nonprofit dedicated to open source digital radio work with a very special focus on amateur satellite work. This presentation is a who, what, when, where, and why about ORI, and then a project summary. We incorporated in California in 2018, and the next year we were designated as a 501c3, or a public charity, in the United States. And we've had very strong international growth, substantial technical and regulatory success ever since. We are incorporated in the state of California. Our headquarters, you could say, is in San Diego, California. This is where our physical location of our remote labs is located, and where most of the shipping and receiving originates from. Our volunteers come from all over the world. We have quite a few from North America, South America, Europe, a few in India, and a number in Japan. Our daily engineering goes on a Slack workspace of about 300 members, and we have an email list with about 280 members. The community is informed through our Inner Circle newsletter. We have about 2,000 subscribers. There's a very simple sign up with the QR code at the right. All of our work is published in GitHub. We have 73 repositories as of today, with 99 contributing members. Our project meetings are usually on Zoom. They are recorded, edited, and published to our YouTube channel. Our website is openresearch.institute, and we're on most social media. Our presentations and showcases and exhibits and demonstrations have been made in Europe, Japan, and North America, and we generally publish articles in ARRL's QAX magazine and just directly in our repositories and our newsletter and on the website. So why? Well, we formed in the very beginning because of bad experiences. We wanted to do digital communications for the amateur satellite service, and there was quite a bit of resistance to this. And we thought that we needed an ethical space for people to work together on digital communications. We needed an enforced code of conduct to make it kind of a safe space for folks to feel comfortable volunteering together. When we say open source, we are using the formal definitions as defined and licensed by the Open Source Initiative. And this is an organization that looks at open source, the definitions, and says, okay, these licenses for this hardware, for this software, are open source licenses. So when we say open source, that's what we mean. When we say amateur radio, this is as defined by international regulatory bodies. We believe that the technical and regulatory heavily depend on each other. And since there wasn't anyone doing what we believed needed to be done with respect to some regulations from the United States, ITAR and EAR, for international amateur satellite collaboration, that was our first priority. and that particular regulatory reform was our first successful project. In 2022, we widened our focus from amateur radio to open source digital radio. So we kept our focus on open source, formal, and we decided that we would tackle digital radio of all types. So the traditional modulations, iterative receivers, adaptive coding and modulation, polynomial phase implementations, error correction, and more. This new focus on digital radio has been super positive. One of the things that we've noticed is that if you approach people, come at them as an amateur radio organization, that people do tend to kind of make some assumptions about amateur radio, fair or not. But when you introduce amateur radio in the context of digital radio, that you get a lot of enthusiasm and you get a lot of new people that want to join, learn more about it, and become licensed. So we think that that was a good approach. It's worked for us. Our organization is composed of volunteers. They're the most important. Project leads, outside collaborators, other organizations, agencies, funders, and then the directors and the executives. We're not a member society, so membership is free, and you get membership by showing up, doing your best, and being ethical. The leaders serve the volunteers. The leaders provide resources and remove roadblocks. People are met where they are in terms of their technical ability. And we often say, you do not have to be an expert to join, but you do have to be willing to become more of one along the way. We have a few to dozens of volunteers active at any one time. As you know, volunteers come and go, and some can afford to spend the time for a little while and then may have other things to do. And some volunteers are very, very active. So we accommodate volunteer schedules fully. Project leads will have in the range of 5 to 10 at any one time. Outside collaborators, we've had 7 major organizations over time and 5 currently that are sort of more formal collaborative relationship. We have 5 directors. We are open to more. And we have 3 executives. These are 3 individuals that have agreed to serve as the executives for the corporation. And we are open to more. What are we? Well, we are 100% project focused. We're an open source research and development firm with a relatively flat organizational structure. When we say research, we carry that out under the principles of open source and open access. And research is explorations, experiments, whether theoretical or practical. We also do development, and this is turning the research ideas and the theoretical into practical, things with molecules, hardware, software, firmware, all of which needs to contribute to the advancement of the radio arts. We are very focused on demonstrations and deadlines and documentation. These are things that motivate people to finish things and to move things forward. So we also have products. So we have the research and the development, and we also have a few products. That's our trans-ionospheric radio peripheral and the current RF Bitbanger digital QRP kit. And we look forward to future products coming along over the next year. When we talk about development, research and development, these are things that we achieve through open source. So we're fully dedicated to open source projects, and we firmly believe that this enriches people's lives in at least 3 ways: personally, professionally, and educationally. So our work is used in both commercial and non-commercial ways. There's no restriction placed on the way published work is used, and we've been delighted at some of the uses of our work. The only real restriction that we have is that we do not allow participation for the purpose of creating weapons or for national defense. This would expose us to regulations and realities that would really prevent or chill international collaboration on our products. So that's the only real restriction that we have to be mindful of. This is a list of our projects. From top to bottom, it's small to large, and generally from inexpensive to more expensive. There's 11 formal projects. We do have a number of other projects and investigations going on at any one time, but these are the ones that are actually named where we have reports on them and dedicated folks. Now, the ones that are of most interest to AMSAT UK would be the ones in bold. So Hypharia would be the space segment side. That's what's up in space, or the central node for the communications that we're talking about today. And that would include a polyphase or multi-rate channelizer. And then opulent voice, that's the uplink protocol for our space. It can be used either terrestrially, point-to-point, or in a multiple access situation like with this particular design. And remote labs, which is where we have equipment available for volunteers to use, so they do not have to buy expensive software, hardware, licenses, things like that. And then worked in here as well is our regulatory work. So that is absolutely important for collaboration moving forward. Regulatory activity, hand in hand with the technical. This is a list of all of the different major achievements and things that we have done, either completed or are actively doing. Remote labs, this is what it looks like. So you can see in the photograph on the left that there's a wide variety of network accessible RF equipment. And what comes with the lab is lab techs, and we have a number of them. I'd like to introduce you to Lab Tech 3, and she is here at an ORI birthday party, so we had a celebration in the lab. Her work was to characterize battery curves for NiCad cells. And the reason that we investigated this is because of the past success of NiCad batteries in space in amateur projects. And this wasn't documented terribly well or really understood. And we had some ideas that, you know what, if you characterize the charge and discharge curves very carefully of your cells, that you can pick ones that have a similar set of curves and that they'll behave very well as a battery. And so she handled this project and learned how to write code in Python, learned a lot of math, about batteries, and also about math and curve fitting. And this sparked an interest in engineering, and she's now a EE major at university. So this is the sort of thing that we try very hard to do: meet people where they are, give them real projects to work on, things that actually can be published, that are actually things you would do in amateur radio, either from a historical perspective, trying to get good documentation, or innovative work that hasn't been done before. The link down at the bottom of this slide will take you to details of all the equipment, network architecture, and remote access to our remote labs, which we are very happy to help anyone duplicate. If you would like to set this sort of thing up, we've done an awful lot of work to make it work for us, for people, make it accessible. Now, on the very top layer of remote labs is the FPGA and radio development boards. And as of today, here are the two that are actively connected to the lab, along with a number of Pluto SDRs. But these are the kind of the larger FPGA and more advanced radio chip versions that we have. So what we're currently using with our projects. The one on the left is a ZCU 102. That's a Xilinx UltraScale Plus FPGA, pretty large, with the ADRV 9002, which this chip is low power, still 40 megahertz wide bandwidth, but it's more for mobile radios. Now, the one pictured in the right is a ZC 706, which is a very large 7000 series FPGA. And the ADRV 9009 is a base station style radio chip. Okay, so that covers a lot of space. And these are large enough FPGAs for advanced work. We also have all of the licenses that you need in order to use them. So a full floating license for Vivado. If you have open source solutions that you want to use with these chips, that's totally fine, but we provide the industry standard license. We also have the full license from MATLAB for all of the toolboxes so that you can do any sort of simulation or checkouts of any of the digital communication techniques that you might be interested in. And this is where they're located. And this is how we generally talk in the lab. Over short distances, we use like PCB antennas. This one's from Kent, Britain, and that's pretty much what we do when we're working in remote labs. So if it's not actually connected over a cable from transmitter to receiver, then we're going short distances over the air with these styles of antennas. So when we talk about opulent voice, this is our uplink protocol, and it is minimum shift keying modulation. It has a 16 kilobit per second high fidelity voice codec. We use Opus and opulent voice, not an accident there. It transmits data and voice without having to switch to a separate clunky packet mode. That was very important to us because we did not like the way that most amateur digital voice modes worked, where you had to switch to do data or images or keyboard. We wanted it to be very modern and efficient, and that's been achieved. This is what it looks like when you are working on FPGA designs. You are describing in software something that will exist in hardware with lots of signals and all of the different software techniques. And this is one example along the way of checking things out. So each of the signals is simulated and confirmed to be working before we try it on hardware. As you know, this is just one part of the process. Once you get to hardware, you usually discover all sorts of other things that may not have been anticipated in the simulation step. So we help people manage this process, going all through from the basic idea to trying ideas out in maybe MATLAB or on paper or a whiteboard, to writing the code, to simulating the code, to preparing it for testing in hardware, and then setting up the tests in hardware, because the visibility that you have for the signals from simulation to actual integration is different. And we support people throughout that process. So opulent voice status. The modem now works over the air, and has the modem, earlier version, has been deployed twice on sounding rocket projects, the RockSat-X project with the University of Puerto Rico and a couple of other universities in the lab, and have tested it with different satellite projects. So it's we're very proud of that, and it's really wonderful to work with students and to teach them minimum shift keying or basic digital communications. Super rewarding. Opulent voice, when you look at the code, is composed of reusable VHDL modules. All of the modules are available on our GitHub, and if you go to the link in the middle of the slide, you will find the implementation for the Pluto, so targeting the Pluto SDR. So this will give you the design of one. This makes it even more useful, less filtering, and more precise control. So that was one of the steps along the way, was going from real to complex baseband. The digital loopback was the first thing that we tested. So this is all inside the FPGA. We're still in digital math land, and we had to make sure that what we were creating, signal that we were creating, was what we expected to receive. Those tests passed. Then we went all the way out to the antenna and did an RF loopback for what's called PRBS, and this is a pseudo-random binary sequence. So that's one of the modules in there, and what it does is just creates a random-looking signal, and that worked. And then we moved to providing arbitrary external data, the things that you would send over the air. And that is now working with a tiny little asterisk, because it looks like, you still need things like a preamble, sync words, and stuff like that. So we are now exploring kind of like the stability of the loops in the demodulator. All that's very active, but the data that you receive is what you sent. So for this minimum shift keying version, for the latest port from the Pluto SDR to a larger FPGA, all of that is going extremely well. Why do we need a larger FPGA? Well, when you start adding things like a framer and a deframer, forward error correction, randomization, interleaving, things like that, you're going to outgrow the relatively small FPGA in the Pluto SDR. And we did. So we bit the bullet and we ported it over to a larger FPGA. This now gives us the chance to include not just the transmitter on the ground station equipment, but the satellite receiver up in the air. That's called HiFiRIA. This is the uplink receiver on the satellite. It's an open source, multi-rate receiver, and it leverages work from a really neat project, an open source project called Theseus Cores. So they implemented a polyphase channelizer and a polyphase synthesizer, and we took their work and used it to make our design better. So this is in the progress of being implemented on the Xilinx UltraScale Plus processor in our lab and using the 9002 radio chip from Analog Devices. And on the right is just one of the many diagrams that we've made along the way to kind of record the channel plan. Okay, but wait, there's more. The human radio interface is very important. How you talk to the radio, how the radio presents the data back to you that you can use as a human, kind of key. And our human radio interface is called Interlocutor. The website takes you directly to the source code. It's a set of Python scripts. It was designed to run on something like a Raspberry Pi 4 or any other computer with a little bit of fiddling. So you have your microphone, a speaker. You're able to chat through a keyboard. You have a display. You can use a command line interface. You have configuration files to start up your radio exactly how you like it, and a web interface. So your opulent digital voice frames are interleaved with keyboard chat, control, and data. And it just works with priority queues. There is no separate clunky packet mode, and the audio is beautiful. 16 kilobit per second Opus codec is much higher quality than Codec 2 or Ambi. This is what it looks like. So you can run the radio from a command line interface if you want to, and all of the functions will work. Or you can call up the web interface. You access it through any browser. You can even use your phone if you want to. It's HTML5, JavaScript, and CSS. This is the communications tab, and it shows you the central window and where you type on a keyboard. You can have a push-to-talk button in the web interface, or you can use a hard button in on the Raspberry Pi. It's designed with accessibility from the start. On the screen, when you receive audio, you are going to hear it. It's going to play through the speaker live, but you also get what we call an audio replay. So a little UI bubble will appear, and you can replay the audio by clicking that. There are audio transcripts available as well. So if you need to not hear anything or cannot hear, then you can switch on audio transcripts and it will print out what the audio said. It's done locally. There's also text to speech. So if you can't see very well or you cannot spend time looking at your screen, then all of the text messages can be turned text to speech for you. We have been making a huge effort to be compliant with accessibility standards and guidelines, and all of the developers for all of this code are fully committed to doing just that. Anything that improves the accessibility for people that may not be able to see or hear or have other distractions or have motor challenges, we want to make it as easy as possible, and that will help everybody. Now, this is a configuration tab. Config files are edited and saved and loaded and checked for errors on this tab. Some of the changes require a radio restart, but the goal is that your radio starts up completely configured. The configuration runs from top to bottom in the order of most important down to least important. Like, most important is the file name of your config file, your station ID, who you're talking to, the IP address of who you're talking to, because this connects to the modem over IP address, or to other computers. You can talk directly to a computer, and the audio and all of that will show up. Further down is kind of the danger zone of things that you might want to experiment with or customize. But wait, there's even more. Interlocutor will deliver the data frames to the IP address of your choice. Like I said, it can be another computer running Interlocutor for like internet-based communication if you want, but we want to talk to a radio. What helps our radio frames get to the modem? And this interface is called Dialogus. The source code is here. It's an embedded C program that runs on the ARM processor in the Pluto SDR. It takes modem frames delivered through the Ethernet USB port and delivers them to the modem in the FPGA. So it handles that crossover from the programming side, the processor side, to the FPGA fabric. Frames come in from anywhere, and the data, over the IP address, and then the data is delivered to the modem. The modem's called Locutus, and it's in the FPGA. The received waveforms over the air are turned back into baseband frames. They go from the FPGA to the processor side, and the dialogus handles them going out to the Ethernet port to the human radio interface, or interlocutor. And finally, we do have a demonstration conference server. If you want to see what it would feel like to have a satellite with all of this code running on it, then our demonstration server is called Locus, or the code base is called Locus. Totally open source. It's a Python script that runs on your Linux server, and ORI has a Linode instance set up and running. You can connect to the IP address of Locus. The IP address is right there with your interlocutor program. And then you can hear other operators live audio. And if you have it set up, you can get transcripts, type chat messages back and forth, and see all the control, authentication, and authorization messages. So 2 things that we believe and that we want to bring to your attention. We believe that open source digital radio is the way forward for amateur radio, and that these designs need to be centered in amateur radio work. And you need to give the space and time to learn an experiment with digital communications. A lot of it is hard. A lot of it's unnecessarily hard because it's not taught or explained very well. We really want to help make that an easier process. You can't have digital without analog. Digital exceeds what analog is capable of. It's both and, it's not either or. And we do have to get serious about open source digital radio designs for amateur satellite, and then stay serious about it. The other thing that we want to emphasize throughout all of our designs, there is no room for crappy codecs, for low bitrate codecs. Amateur radio digital voice products for like VHF and UHF, they pretty much have to use very horsepower creation. There really isn't much replacement for displacement. If you have a very small displacement engine, there is a limit to the horsepower you're going to get out of it. Codecs, voice codecs are the same way. This is why we say use higher bitrate codecs, open source ones like Opus. This is why we went with at least a 16 kilobit open source voice encoder for our work. This means that 70 centimeters and above is where it's legal. You do have to give up 2 meters for the most part because of bandwidth limitations. Opulent voice takes up 80 kilohertz, the way that we have it implemented today. If you have any questions at all, please ask me anytime, any topic. I really appreciate the chance to present our work and share it here with you today. You can find me at this address, w5nyv@yahoo.com is a direct email address. Please sign up for the newsletter if you're interested in getting updates and articles and explanations and tutorials about our work. And you can find me on social media and LinkedIn as Abraxas3D.
Well, I think all you can say about that is wow. I got quite lost on the way through there, and unfortunately, as it's a video recording, we can't ask Michelle direct questions, but we can no doubt provide the link at some point on that side with the slides. So I don't know whether anybody wants to talk about any aspect of it on that side just amongst our group, or too early on a Sunday morning after the dinner last night. In which case, we are slightly running ahead of schedule because this session was going to run through to about 10:15. Then there's a coffee break. So we might all want to take an early coffee break and get some more caffeine in the meantime and have a chat amongst the group, perhaps. Okay? Thanks very much. to talk about APRS weather transmissions via the ISS, which strikes me as a very difficult way of doing it. Transmissions via the ISS, which strikes me as a very difficult way of doing it. But anyway, over to you, Ian.
Okay. As most of you know, I'm Ian Young, G7II, as Barry just said. The RSGB, yet again, didn't manage to spell my name right, but that's not changed in years. So yeah, today I'm going to talk about weather stations and uplinking to the ISS. To be honest, this presentation could have been called Ian's Lash Up, it could be called Ultra Portable Operating, and any number of other topics, but I decided to keep it simple. It's divided into three areas. The first one, I will be talking purely about the weather stations, but that will hopefully only be a minor part of the talk. The bigger part will be discussing how we get those APRS packets up to the space station, and then the third part will discuss future evolvements that I have planned and one or two future ideas that turned up on Thursday evening, so I haven't had a chance to really let them distill. So it's much more going to be notes on what I've done so far and what I'm planning to do, rather than any very polished talk. So with that said, let's get started. Just a quick agenda, and I've already covered this, but a couple of extra things that I didn't mention. Well, one thing I didn't mention was the LoRa to Wi-Fi gateway, which I will discuss, but is really only at the design stage at this point. And by the way, just for the record, so what about the weather stations I've got? I've actually got two here, and you're more than welcome to come and take a round. Powered by a Raspberry Pi or an Arduino Nano ESP32. Essentially all they do is read various sensors, and I'll go through some of them in a minute, format and generate the APRS packets, and the weather station itself, the initial design was to send it via the internet, via Wi-Fi. So that was the initial design. Now, the first one, which is affectionately known as weather station number 1, is a Raspberry Pi with a very nice sensor board on it. It's powered by a solar panel, and this solar power manager, as WaveShare call it. Basically, it's three 18650s, each of 3,000 milliamp hours. The charger has a socket to connect the solar panel, so it can charge the batteries. It also has a socket for shore power and to feed the Pi and the sensor board. Now, this sensor board is very nice. It has about 7 or 8 different sensors on it, from pressure, temperature, humidity, UV. And again, there's temperature, humidity sensors there. There's pressure. There's a lightning detector as well, and a few other bits and pieces. Now, again, it uses the same solar power manager, but this one, which is affectionately known as weather station number 3. Weather station number 3 is powered by one of these things, an Arduino Nano ESP32. Yes, these both have GPS receivers. What else can I do? There's going to be no 2-meter stuff around there whatsoever. You're in the middle of the Highlands, so what can I do? Well, I took a look at the ISS passes for one of the holidays that I was planning, just before the issue with the ankle turned up, and checked the passes, and yes, we can see the ISS at times. So I thought, why not? You know. So How do we uplink to the ISS? Well, uplinking to the ISS is no real different to any other iGate that you might run. Only difference being one of the radio ports is on 145.825 rather than 144.8. Yeah? So, you know, it's, as I said earlier, it's not as hard as Barry was fearing. Yes, you do have Doppler effects and all the rest of it, but to be honest with you, I've uplinked just with a few watts, just any old ISS pass and just any old APRS packet in the past, so I know it can be done without, you know, huge antennas and so forth. The plan, because I want to be ultra portable, is to use a V dipole. Now, a V dipole is a horizontal V, and you aim it north or south, depending on which pass you're covering. All of this gear needs to fit in this, you know, and that's the largest rucksack you can get. It's an 80-litre rucksack, and to be honest, I couldn't carry 101 anyway. So, how do we build the iGate? Well, and actually do the uplink. Well, I think most of you probably recognise these two. One's a Raspberry Pi 5 on top, and a Pi 2.0 on the bottom. Important to note that the initial iteration of this was very much designed to be shore-based, using shore-based power, just for convenience and ease of build and testing. However, as I say, you all probably recognise these two. Who here recognises the two radios on either side of the Pi? Yeah. Now these are, and I've got one here. I only brought one to cut down on weight. Yeah. Now, why use such an old radio? One, they're built bulletproof. And if you're going up into the Highlands, one slip and you're going to be falling over and damaging the more fragile radios. There is another reason. If you take the batteries out, which I have, they're long since died anyway, being NICADs, you can power it on and off via relay. That is harder to do with some of the more modern rigs with you know, things like the TID radios, which I adore. I've got 4 of them. You know, because they're always powered when you've got the battery pack plugged in. Now, because I'm trying to go as low power as possible, I don't want the radios on unless they're actually transmitting. Yeah. The design, as you can see, uses USB sound cards. Yeah. In fact, this Pi is also controlled by a relay. The microprocessors fire it up when they want to transmit a packet. It then transmits the packet and shuts itself down again. Now, what are the considerations when transmitting a packet? Well, the initial design was, okay, I'll transmit one every 15 minutes just to get the design up and going. I have about 4 criteria. That is one of them. If it hasn't transmitted a packet in 15 minutes, it will send a packet, but not to the ISS. The only time it will send a packet to the ISS is if the ISS is above the horizon and it hasn't heard its own packet. Now, that needs a little bit of scripting, but I've got that script on some server somewhere from the past. The other time is if there is a lightning strike detected. Yeah, that's the 3 criteria. This helps save power, which increases the longevity, and it also stops me spamming the ISS. And so I think we've already been through this slide, why the IC02. And again, if anybody wants to see one in the flesh that hasn't done, there's one here. And so, one of the problems with going up to Korea is, yes, they have Wi-Fi, but I have tested it. It's not great outside of the station house. Literally, I walked out the door and had no Wi-Fi whatsoever. So, one of the ways to get over that is the LoRa to Wi-Fi gateway, which is only on paper at present. Just because I haven't time to actually build it, I do have the bits, but I haven't built it. And so what would happen there is the microcontroller would get a SPI-based LoRa board, and a second microcontroller that's already got Wi-Fi on board would also get a LoRa board. The weather station would transmit the APRS packet in text format across to the second microcontroller, which can then uplink it to APRS-IS, or can pass it on to the ISS gate. So, yeah, okay, I'm right. I'm going ahead a little bit there. So, now one of the things I'm looking at doing is merging at least 2 of these 3. Yeah? There is no reason why I couldn't have the weather station and the radios under the control of one microprocessor. There is no reason why I couldn't extend the LoRa gateway to include the ISS gate as well. That's all, for the future. Yeah? So, any questions so far? Okay. Now, on Thursday night, when I was looking for some artwork to add to this, I came across this, which maybe it was the wine, but it got me thinking. We obviously can't do APRS over AX25 via QO100, that's verboten. However, what we can do is PSK. I found this by chance. So, as I say, it was only Thursday night, so I've looked at the blurb, and that's about it. Whether I believe it or not, I'm not sure, but it claims it's got 12 dBi. Now, 12 dBi gain, couple of watts, 2.4 gig. I think that could work, and it's lightweight enough that I can stuff it in my bag and not worry about the additional weight. That combined with a 60 centimeter dish would give me a QO100 station that I could potentially get up to Korea or Lundy Island or wherever else I fancy going in the middle of nowhere. So that is an idea that is germinating in my mind. So, and again, this is just a pictorial diagram of how that might work. It was only lashed up very late on Thursday night. As I say, that was one of those ideas that came just by luck. Yeah? And so, what else needs to be done here? Well, I've got to add the I2C voltage and current sensors for both solar and battery. As I said earlier, hopefully I can eliminate one of the nodes of the system. Because the idea is that it is portable. And by the way, just for reference, this is actually very slowly charging that right now. So it does work. So yeah, that's the quick version, of the plans and of what I've done so far. As I say, the next thing will be getting the sensors into this thing, and I'll just put the mic down for a minute, and I'll show you that. You basically do that, and then you have a nice area to put the sensors in. And yes, that is a piece of N-gauge railway I had lying about. It happens to be the exact width I needed, just to do some basic fit checks earlier this week. Yeah, and so that is planned for probably next weekend. Some people will be wondering why the ESP32, because it is extremely low power, and you can turn its peripherals off, including the Wi-Fi, and only bring them up as and when you need them. So it can sit there monitoring the sensors, and when it detects a condition where it wants to send a packet, it can fire up its Wi-Fi, it can flip the relays that are also going to be on the I2C bus, and then it can fire up the radios from there and send the packets on. So with that, I know that was short and sweet and quick, but does anyone have any questions or want to come and look at some of the gear?
Thank you. I think you said this was called a Stevenson enclosure.
Yeah.
And where would you purchase that from? Because I know everything else.
Right. That particular one I found at Paimori. No affiliation whatsoever. I was just looking for them, and I didn't want one of the big ones that the Met Office use. So I pumped in tiny Stevenson enclosure, and that one came back. About £13.50, I think. £13.50.
Any other questions?
Hi, Ian. This was really great, really thought-provoking. I was wondering if this concept could be expanded to other APRS spacecraft, or is that something you
we'll talk to other APRS spacecraft as well. All APRS-capable spacecraft respond to the 2-call AR-ISS. So it will automatically do that. You don't have to do anything with it. I just picked the ISS because that's the reliable one, and I knew that I could see that from Korea. As I say, originally I was going to take this up in June, but then things happened, and suddenly, yes, that wasn't possible. So now it will an evolved version will be at EMF camp. So expect that, and then I've got another trip to Korea planned in August, so that'll be the real test for it and me, to be honest.
Thank you.
In that case, can I ask that we show our appreciation to Ian for putting his thoughts together and telling us? Okay then, everybody, welcome to this presentation. We've got Patrick Wood, who's previously a CEO of SSTL, a veteran of military satellites as well on that side, and also an amateur himself with an amazing array of equipment here now, who's going to tell us about his work with SSTL and small sats and the CubeSat simulator. So over to you, Patrick.
No, thank you very much. Thanks for the opportunity. Start with this slide on the screen. This is not the one that's publicly used. The one that's publicly used, the panel on the spacecraft is actually in place. So this was just like a few minutes before. These are DMC-3 spacecraft that while I was the CEO, we delivered into orbit. They're 1 meter resolution imaging spacecraft. But it's just interesting to see, fundamentally, to position them 4 very large reaction wheels, all orthogonal to each other. The 4th one is a spare, really, so and it can sort of mimic any of the other three. But actually, sometimes it's you don't have a huge amount of electronics in spacecraft. It's the size of the spacecraft is really driven by the fact that the imager goes from the top to the bottom of the spacecraft. So that one is normally one. If you Google it, you'll see the one that's on the internet, which has the panel on it, which is just as exciting, but maybe not if you build spacecraft. So if I go to the second slide, I could probably talk about those 3 topics for probably about a day each. So I'm going to try 15 minutes on each topic. So you have to be tough on me on timing. But I'll just give a little bit on space history because although I've done a lot of small satellites with SSTL, I've also probably spent a lot of my time doing larger spacecraft, and hopefully I'll rush through to get onto CubeSat simulator, which we've got a live demo of 2 CubeSat simulators here. So hopefully we can actually do some experimentation with that, particularly on the slow scan TV. That's what I'm trying to get to. My career, I've just retired. So I retired in April from Airbus. So I was my last job was Senior Vice President of what's called Manufacturing, Assembly, Integration and Test. So I ran all of the production facilities for Airbus on the space side across Europe. So Toulouse, Stevenage, Portsmouth, Madrid, Munich and Friedrichshafen. A really fantastic job. I got to see all of the ESA missions that we were building. Galileo second generation. I'm probably one of the few Brits that's actually seen Galileo second generation because following Brexit, that's a Galileo first generation that SSTL built the payload. I also I was the CEO of Surrey Satellite for about 3 years, and I've also worked for Lockheed Martin Space as the head of space for the UK. So had quite an interesting 25 or 30 odd years in the space sector. The video that you're probably all watching is actually Skynet 5A launch. I was the program director. It will hopefully restart, and I'll just give you a quick insight into launching. It's an Ariane 5 ECA launch vehicle. Launched it from French Guiana. 13 seconds to go. At 7 seconds to go, in fact, in precisely 7.1 seconds to go, they'll fire the main Vulcan engine. And then that engine stabilizes for 7.1 seconds. And then 740 tons leaves the launch pad in 100th of a second. It is phenomenal, the amount of energy. It's a future where I've got all the high-speed video of the launch, and I can tell you, our project team, we spent an afternoon just re-watching it because there's the high speed of all of the fuel cables disconnecting, all the umbilicals. But we did catch the team when we were launching it. We had a team at the launch site, and in one of the bunkers in Corsham, we had the satellite team. And just at the right moment, my head of production shouted down the radio, just in a kind of offhand way, said, "Oh my God, we've lost umbilical, we've lost data, we've lost telemetry from the spacecraft," and then we just didn't say another word. And it took them a few seconds, and they went, "Well, of course, the spacecraft's left the launch pad connected to the launch vehicle." So we did get, even in all these really tense periods, you do get humour. I think if you haven't got humour, building spacecraft is very, very stressful. I'm not going to go through my career, but it started a long time ago. I did electrical engineering, actually. great fun. I was looking at the VMARS display downstairs. I used to work for MEL, and there's a PRC 319 radio. And actually, for me, I've never seen that anywhere other than a classified environment. So now it shows my age, actually, because it's now sold off as effectively surplus. So I started in electronic warfare, did a little bit in medical electronics, but effectively, the rest of my career has been in space. And I've had the pleasure of working in navigation, ISAR, so that's intelligence, surveillance, reconnaissance. Military SATCOM, you could probably see slightly dominated by military SATCOM. I worked on Skynet 4D, E, F. I was the program director on A, B, C, and D, 5, Skynet 5, A, B, and C, D. And then, having just retired, we're currently building Skynet 6A, and we're obviously talking about to the government about future military. But in fact, Airbus themselves also work on the French, the Spanish, and the German military satellites. So I've had the pleasure of working right across that. And sometimes you get those opportunities. I was in the Toulouse factory walking around with the German project manager of Satcom BV, which is the German equivalent of Skynet. And he was sick of me showing him Skynet equipment and going how wonderful it was. So he found the UHF antennas, which are quite long. This is the size of a sort of single-decker bus in the middle. And he pointed to that and said, those must be my UHF antennas. So with great pleasure, I said, no, those small ones over there are yours. These are mine for going on Skynet 5A. Very great friend of mine, to be honest, but, I won't bore you with the rest of my career, other than I'm quite excited about launching. So I put a section on launchers at the bottom. And I've obviously, in my time as a program director, bought launches on a number of Ariane 5 ECAs. So I'm quite excited about Ariane 5 ECAs. That was 5D's launch, which was we left it on the ground for a bit of time. And this is my period of doing Galileo launches. So I've actually had the pleasure of doing dual and quad launches of Galileos from French Guiana. And you can see I've put a little person size, so you can see the size of a Galileo spacecraft. But I'll come back and talk about that when we get to SSTL. I'm rushing a bit. This slide I do for STEM lectures just because it is amazing how often people don't really understand spacecraft. So here we have an animation of the Earth rotating. It's not a perfect animation. I'm sorry, it's not a sphere. It's just a flat picture. But it just gives you the right image, because then you can put a LEO satellite on and you can have that discussion that says, oh, look, every time it comes round, it's going over a different area of the Earth. And I think that starts to give some of the problems and challenges that we all face when you've got the ISS coming over and you're trying to explain you've only got 3 passes that are reasonably decent. Now, because I use this generally, and we're really only talking about low Earth orbit, I will show you the rest of the animation just for fun. So I'm building a navigation constellation now in MEO, and because I work for Lockheed as well as Airbus, I've been involved in Galileo and obviously GPS-3. So I'm quite fond of navigation systems. But I'm also quite fond of unusual orbits. So here's a highly elliptical orbit going out to 36,000 kilometers and perigee of a few hundred kilometers. If you Google, you'll find a video of me talking on the BBC when Cosmos, the Russian satellite, impacted at 90 degrees to Iridium 33. I just happened to be in London at the time, and they put me on BBC, ITV, Channel 4, and explaining that it was a highly elliptical Russian that impacted into a low Earth orbit, Cosmos. That was probably in 2009 or something like that. And then this is probably the orbit I've built more hardware for than anything else, the GEO orbit, 35,786 kilometers. And from a STEM point of view, I show the 3 spacecraft, so you can have that conversation that with 3 GEOs you can do global communication. So that's the end of the education. So, going to do one more press. There we go. In my job, I still actually talk to the US, UK Space Command quite often. And one of the things that they did recently, so I just quickly put this slide in just from a a space interest point of view, one of the things people are really worried about is other nation states doing observations of spacecraft. And so what you want to be able to do is understand how to do it. So the US Space Force actually went and did an observation of Skynet 5A. Quite complex to do that in a geo orbit where you've got billions of dollars worth of telecommunications satellites. You can't afford to make a mistake. But I will come back on that when we talk about CubeSat. There's a reason I put that slide in. Just checking, I'm rattling through these. This slide, for me, I'm super proud of the UK space sector. It doesn't probably get enough kind of publicity as it should do. These are two companies. This is Airbus and SSTL. So SSTL is all these slightly dark green. What a fantastic tradition, Surrey satellite technology. Started by Martin, who's one of my heroes. Was my chairman when I was the CEO, and someone that has just got encyclopedic knowledge of spacecraft. And so working with him and hearing all these stories about the early launches from Kazakhstan and Baikonur and buying SS-18 launch vehicles and not knowing whether there was how radioactive the rest of the launch vehicle was. So they decided we better bolt the spacecraft on pretty quick and not spend too much time. Great stories from this period. I was the CEO around this period, so those are the 3 DMC spacecraft that showed on the video on the first slide. But I've got some specific SSTL slides, so I'll come back to that. But I probably spent most of my time up here building large geo telecommunication satellites, and that's probably what I'm most known for. The red ones are all the military ones for the UK, dotted through time. But if you take sort of going back to megabits per second, up here we're now talking with some of the LEO constellations at terabits per second. I mean, we are, it's almost every 10 years you move the decimal point. And I don't think that will change. You just keep on going. It's incredible. But back here, it was all about building waveguide payloads. Up here, it's all about digital DTPs, digital processors. And it is literally, that's one of the things that excites me about CubeSat Sim, is effectively now it goes straight from a Raspberry Pi through a bandpass filter to an antenna. So these days, it's not about complex RF. I'm a digital engineer, by the way, so it's every time we can avoid waveguides. Although one of the jobs they made me do was run the passive and active microwave group, and that was a challenge because that was like a black art. But I know more about silver plating waveguides than I ever wanted to learn. I also use this slide particularly for the government. To remind them that we have a massive heritage in launch vehicles, which they seem to have forgotten, that back here, Blue Streak, Europa, Black Arrow, and although people go, oh, Europa was not a success, it was from a UK perspective. Stage 1, which was the UK one, worked every time. What the problem was the system engineering of putting all the stages together, and that forced ESA to rewrite and come up with the ECSS standards and change the whole way they did program management and system engineering. I've got to get onto SSTL, so I've got to get... I talk a lot about debris, space debris. I get asked a lot of questions. It is becoming a huge issue. You just look at the number of Starlinks that are deorbiting almost on a daily basis, 2 or 3. And the issue really for the Earth is what's all that, the impact of all that aluminium, particularly aluminium burning up in the upper atmosphere, but also some of the rare metals that are part of that. So I'm not going to go into a huge amount of detail. This is out of date. I mean, as soon as you write a slide on how many active satellites, it is out of date the next time there's a Falcon 9 launch. Because in 2025, Starlink launched more than 2,000 spacecraft. So this slide is a year out of date. That's somewhere around 12,000 active satellites now. And the LEO ratio it's somewhere, in fact I added it, it's greater than 93%. It's a huge domination. And you can see from this picture, you can see that kind of halo around the Earth. That is the LEO debris. And a lot of it historically is over 500 or over 600 kilometers. So its deorbit time is going to be hundreds of years. So if you're in about 550 kilometer orbit without propulsion, you probably will deorbit within 25 odd years, which is the normal international standard. But above that, you're probably into decades longer. The other one, I deliberately put this slide together and used it to give a little bit of an indication to the space agency. I mean, the number of objects that are being registered is just phenomenal. You look at the Starlink, Kuiper, you look at OneWeb, and I was involved in the production of OneWeb. Just the sheer number, the Chinese LEO constellation. But the diagram on the right is a bit of a sobering one, and I'm talking to some of the non-exec directors of UK Space Agency at the moment, just to help understand that a lot of those are no longer UK companies. So although they were launched as UK companies, there's a little bit of a challenge now. This is now a French company. This is also a SES now. Fantastic company. I've built a lot of spacecraft for SES, but I think we do have to protect and defend our space industry. And then one final, next we're on to SSTL after this slide. Launches, I'm super excited about a small launch, UK launch. It's fantastic. We started in 2014. I was in the very first meeting where the minister announced it. We're almost there. I was one of the first in the space industry to be up at Saxavord. I walked on the peninsula with the farmer, actually, and he was asking me all sorts of questions. He said, will I be able to keep my sheep on the peninsula during a launch? And I sort of went politely, no. I think you will need to... but I did then tell him that his house, which was just down on the bay, has fabulous position, his house. I said, you'll be able to sell the back garden to the BBC for a significant amount of money because that's got the perfect camera angle onto the launch vehicle, onto the launch pad. But fantastic. I hope RFA are successful. And it was really interesting to hear AMSAT Germany, actually, Deutschland, actually go through and, they've got some great plans. And so fingers crossed. We've had some challenging, non-operational. Prestwick have just cancelled. Sutherland is paused. So we've got some challenges in there. I know one of the other three is close to making an announcement. It's not for me to say anything. So, there is still a lot of interest in low Earth orbit UK launch, but the size of the spacecraft are growing rapidly. So if you take a OneWeb spacecraft, it's about 150 kilos. Current generation Starlink is over a ton, and they're talking about some of the other ones being somewhere between 700 and 800 kilos. So actually, small launch vehicles become really challenging because you just size of the fairing and the launch mass, but again, fingers crossed. And you can see Saxavord actually have taken that into account, and I think they are licensed now up to 1.3 tons, which is ideal because that's still in exactly where the manufacturers are wanting to build. So I was worried about, it's 15 minutes in, I was worried because I could talk about those topics for days. But I want to talk about Surrey Satellite because this is an amazing UK space company and based in Guildford. Came out of the University of Surrey, one of the most successful spin-outs from a university. Sir Martin Sweeting should be super proud, and I know he is because this is one of the real success stories. It's got two buildings, fundamentally. They've got their office block, and they've also got their production facility, and that is an amazing. If you get the opportunity to have a walk around their production facility, it's amazing because it's got everything from surface mount, but it's also got clean rooms, and that first picture was in their main clean room. So it's a completely vertically integrated factory. Employs about 400 people, and they've launched 74 satellites to date, which is an amazing record because they're not some of the smaller ones. They're typically 100, 200 kilo, 300 kilo spacecraft. And they've built their own attitude and orbit control software and hardware. So they really not only build and integrate other people's equipment, but they actually design and build their own reaction wheels. They built for the DMC mission that was on that very first slide, a 2-axis rotator for the Ka band feeder. and so completely built themselves, because buying it on the market would have cost them too much and they would have made less money. So fabulous company. It is owned 100% by Airbus, but the mission that Airbus has is to try and keep it as a really arm's length company. I started to be a director in 2008, so I stepped in onto the board in 2008, and then I became the CEO in 2014. So and then I was the CEO for about 3 years. So I've had a long heritage with SSTL, and as I say, I love going around the factory. Andrew Cawthorne, who is the current managing director, I sent him a note saying I was doing this presentation. Could you send me a few slides? So these are actually SSTL slides I've embedded into the presentation. And I thought I asked him for some slides or some pictures from my period. So that's a flat sat version of Galileo. So you can see the Galileo payload. They built all of the first generation of the payloads for Galileo, including integrating the antenna and the search and rescue beacon. If you look at a Galileo spacecraft, there is the main navigation antenna, which is a phased array. And then there is a search and rescue receiver on the spacecraft, which is these nodules at the top. So if you're in the middle of the ocean and you activate your EPIRB, your distress beacon, you are talking to that. And that generation added, before you'd activate it, you had no idea whether anyone had heard you. With this one, it actually has a voice channel, so you can actually get some feedback to say, yes, we're on our way, which if you're bobbing around in the Atlantic, it's probably quite useful, just to have some idea that a maritime patrol aircraft is on its way. So really, really good. 2 of the maser clocks, if I pointed correctly. The processor, the payload interface unit, and a lot of the microwave hardware. They built something like 30 payloads, really intense. And OHB was the prime contractor that then integrated it into the complete spacecraft. And OHB then delivered that to the launch site. And as I say, I got the great pleasure of, to start with, they did a dual launch, which is always tricky because you've got to make sure you fire both of the pyros to dispense the spacecraft at the same time so that you don't have a perturbation on the launch vehicle. And that was successful. So then they tried a quad launch. They did it in pairs. So the first pair went off because they knew it was stable enough that the launch vehicle would then have the second pair of spacecraft were ejected. On the same launch vehicle, where have I got to? We also, SSTL haven't built many GEO spacecraft, but they have built one called Quantum, which was a next generation of telecommunications payload. So that one is actually a payload that is capable of being frequency adjusted. So normally, up to that point in the kind of evolution of GEO spacecraft, they were built for a fixed frequency, so they were tuned for a particular frequency. Quantum was the first one where they were actually being able to, in orbit, retune the hardware. So that was quite exciting. And then Carbonite went up on the same launch as the DMC-3 that I showed earlier. So there were 3 optical, and Carbonite was built in 7 months. It was using a commercial telescope. So that is a commercial telescope. When you looked at it, it looked like the barrel was carbon fiber. So they were sort of, okay, fantastic. This should be quite thermally stable. And they put a hairdryer on it, and they discovered it was nylon. It just went all wobbly. So they then had to build their own. They basically took a commercial telescope apart, rebuilt the carbon fiber, reassembled it all, reconstructed the telescope, put it on a spacecraft and launched it. And they did all of that in 7 months. That was, at the time, unheard of. That's what SSTL does best. What they've just launched, Tyche, is an evolution of that very first spacecraft that we were just talking about. This is owned by Space Command. It's basically provides ISAR, intelligence, surveillance, and reconnaissance information for the UK. It's got an imager, which again goes all the way through the middle of the spacecraft. It's got fairly straightforward solar panels and an SSTL core DHS, which is their avionics hardware. So it's a completely SSTL built spacecraft. Really, really fantastic. Got high-speed Ka band downlinks. I didn't need to put a 2-axis rotator on it, so it's just very high speed. So as it goes over the ground station, they've got enough data bandwidth to put the whole imagery. So effectively, as it's going round, it's got a mass memory. It will just store up the imagery, and then it just squirts it down as it goes over the launch site. So really, really great opportunity there. This is what they currently have in build. So for commercial reasons, it's a little bit devoid of detailed information, but it does show the sort of stuff that they're building. And again, typically all around the 200 kilo size, maybe some of them slightly larger, but also some of them are based on 6U CubeSats. So if I go through it, Theos 2A, video imaging. Mostly the imaging world is about static imagery, but there are a few that want to actually understand motion on the Earth, and there are some things that are quite useful. So Theos 2 is video imaging satellite, so it will take video as well as static images. AIS, they often put AIS receivers on spacecraft these days. Often, particularly SSTL, one of the things that they're really known for is doing training missions. So they'll sign up to deliver a spacecraft, but they'll add a training module. So some of the engineers from that country will come over and actually probably go through a University of Surrey education, go through a series of courses, and then they'll actually work on the spacecraft. And that's one of the really unique selling features of SSTL. So when you've built a spacecraft, you've actually also got some people that will go back to the country who understand what it's like to build a spacecraft, and that's so important. So it isn't just about commercial reality of spacecraft companies, it's about how do you add value. Then we got into HotSat 2 and 3 for a company called SatVu. They wanted to have something which got marketed called dark carb. So it's basically thermal imaging. So you don't do it in the visible light, you're doing it in infrared. And effectively you're starting to do thermal footprints of towns and cities or industry. And that's really useful from a climate perspective. So there are companies that want to use downstream applications for that. And there's a company that, as I say, are getting SSTL to build that. This one, CubeSat, synthetic aperture radar. So it's a passive radar. It's not an active radar. And it's one of the new startups in the UK called Oxford Space Systems build antennas that unfurl, and they've done a fantastic job. They came into being about 10 years ago. They really have built some fantastic antennas, and this one is a demonstrator which will effectively deploy. Spacecraft behind it is something like 150 kilo spacecraft, and when the antenna deploys, you've got something like a 5 meter. I think that one actually might only be 3 meters in diameter. And synthetic aperture radar imagery comes down. It's harder to process. If you've ever seen a spacecraft radar imagery, it doesn't. When you first look at it, it doesn't look like an image. But once it's being processed, and some of the clutter's taken out of it. Innovative radar mission called Microsar. So again, you can start to do much larger deployed antennas. If you imagine this is something that's probably around 100 kilo spacecraft. It's been built for Space Norway, but it's got a very large deployed antenna, which is probably in excess of 5 meters. So again, the resolution that you can get on Earth is much higher. Wide swath multispectral imager they're building for a particular customer. But this way, when you talk to them, this is where they immediately start. Actually, I've done the slide in the wrong order. Yesterday, I think it was yesterday, there was this discussion about going to the moon and building a telecoms network around the moon. SSTL are involved in a mission called SSTL Lunar, world's first commercial lunar comms. They're doing all the preliminary work to build that network capability. So super exciting, challenging financially because European Space Agency want to fund certain parts of research. Ultimately, they want to turn it into a commercial mission. but sometimes it's hard to get that through there. But there's so much interest in being able to do that. It's quite fun. Hydro GNSS. One of the things that one particular engineer in SSTL, his hobby is reflectometry of navigation signals. I always say GPS signals, but he can use any. And he's designed a GNSS receiver, multi-channel GNSS receiver. And what he does is he takes the reflected signals from the Earth from the navigation signals. So it's effectively a passive receiver. Because there are quite, as you saw from that slide where the MEO constellation navigator, there's a lot of navigation satellites. So there's a lot of L-band communication coming down. Can you read the reflected data? And he started doing that probably about 10 years ago. ESA missions and getting research and ARTES money and money from the UK Space Agency. And then he started to be able to figure out things like wave heights, wind velocity, just from the reflected GPS signals. So reflectometry is a growing area. It's a bit specialist, but it does show that sometimes in life you have to really think around the subject and see what kind of capability that you can create there. And then Juno is can't really tell you much about Juno. It's an ISAR satellite for UK Space Command. I think I'll just read that out and step on. Fantastic. UK Space Command are relatively new, it's about 3 or 4 years old. They're really going up a steep learning curve. They're taking all of the space domain awareness, space situational awareness. They use topics like, they use facilities like Farlingdales. So they're building up, and they have optical sensors that. So they're building up a space domain awareness for the UK and where we have UK territory around the Earth. So it's a major topic. Quick switch into why do I get excited by radio amateur? I started actually weather APT. It's really sad that 6 weeks. I think it was 6 weeks ago. The last NOAA 15. I've had that antenna in my roof space of my garage for probably a decade. I stopped when, quite frankly, the receiver that I bought stopped working. It's on the next slide, so I won't tell you too much. I love building QFH antennas. I've then got the Arrow 2, and in fact at the National Radio Centre on Friday, I showed that I've got an Arrow 2, which I built the extension to, which is really trying to mimic the Arrow 2 Alaska version, which has got, mine's got about 3 dB more gain. Does work. I tend to put it on a rotator. I'm not strong enough to hold the extension on an Arrow 2, but it's a good solid antenna. So that's a picture without the extension. If I have enough time and get really serious, I've got some very high gain VHF, UHF antennas. So those are you can see my VHF one on top of my Yaesu G5500. So I do experiment with building unusual antennas. I'm not saying that's the best antenna I've ever built, but it does work. It's well, sort of works. Yeah, not everyone is a success. So this is the weather satellites. I've had some decent images down. I used to use a quadrifilar helix antenna, but I found I was picking up a terrestrial interfering signal, which I just could not get rid of. You can't see it on this image; it's just there. I cut the image off at the point where the transmit. It was happening every 2 minutes. So if it takes 2 minutes to download the image, statistically you will get it statistically you'll get a good image, and statistically you'll get one with interference on. So I changed to a V dipole and started to get some really, really good imagery. And the software, the WX software, is really good at stitching imagery together. So you get some really good capabilities there. Last Wednesday, I only just put these slides in. So only a few days ago, the ISS was coming over. And what I showed at the National Radio Centre was my tape measure antenna. So I made a tape measure antenna. I just love, you'll see the tape measures on my CubeSat simulator, mostly because I've seen quite a few real satellites with tape measure antennas on, and I just find them fantastic. If you go and ask the company that make tape measures, they charge you more for the tape measure without paint on it than they do if you just go into a DIY shop and buy one. I suspect it's because they've got to take it off the production line, but I won't tell the company. But we went and talked to them, and they said we really want to buy some nice, shiny, unpainted, and they were going to charge me about double the price of a painted version. So we just fitted one with paint on it. But the ISS was doing the imagery, so I got a really good picture of the Sputnik. I did this all simultaneously. I was waiting. I had all of them lined up. It was a really good west to east pass. So I had the tape measure antenna on the right hand side. I had my extended arrow 2 on the left side of the rotator. This one I just think I picked up some interference, but I used the same Raspberry Pi that is here. So I used my CubeSat Sim Raspberry Pi. So very, very simple receiver. But while I was there, I switched my handheld on, and you can see that's why it took a bit of time. I wasn't. I got a decent image. These 2 bits of interference is because I went, I wonder whether it's working, and put it back. I wish I hadn't done that, but that's life. But it's a good illustration. Actually, yes, you can spend, you can have a decent radio, but with a very flaky tape measure antenna, you still get a good image. So it's good fun. I just find radio amateur just such good fun from a experimentation. And then this is just a zoomed in version, and then the next pass. Interestingly, I've got an interfering signal somewhere, because you can just see, if you look on the image, and there is a regular interfering image source that is causing a problem, which clearly is intermittent because it's not on this one. But the image at the top, that was at 1 degree elevation. I couldn't believe it. The ISS has a very large transmitter. It's 25 watts. But I wasn't expecting, I wasn't paying attention, and my slow scan TV just jumped into life and picked up. That was literally at, well, it says 2 degrees, so 2 degrees elevation. That was, as I say, it does show that the ISS is really useful, particularly if you're getting people to do it for the first time. Right, we're on to CubeSat simulators. I've done it, just about. Low-cost satellite emulator. I started reading about the AMSAT US CubeSat simulator, and it's just a fantastic product. So you thought, well, I've got to build one. I think what attracted me was you could clearly, it's open source, so you can see the payload software, you can see the Raspberry Pi, and you can see the ground station, and they give you sufficient information that you can get in there and modify it. So for me, it was super exciting. Working solar panels, batteries, transmitter. So it's a version 1.2. So I built the one on the far end first. Let's just make it rotate a little bit faster. There we go. I have the sun. I have the sun simulating onto the solar panels. As I say, created by AMSAT US, and I've certainly added to it. So if you take the basic system, it doesn't have the ultrasonics, and when this comes round, it has a laser rangefinder and ultrasonic. I know ultrasonics don't work in space, but it's great for STEM. And what I did was, because I'm interested in rendezvous and dock. What I tend to demonstrate is, when it's static, is that the ultrasonics, I've deliberately in software made it not as accurate as the laser. Actually, they're pretty much similar when you actually go and look at the data. But what I do is I try and go, well, you'll if you know, you go read about the ATV, the Automated Transfer Vehicle. It was a supply ship up to the ISS, which my team in engineering and operations built. They have 5 sensors. They start with a radar, then it goes to LiDAR, then it goes to, I think they have a microwave rangefinder. I'll probably get this wrong. And then they finally go to an optical The very final dock is an optical. When they first docked with the International Space Station, the software was so good that it just came in and it just touched the docking port, didn't do anything. And then someone said, well, it is a Russian docking port, maybe we have to hit it slightly harder. So they backed it off, and then they basically just drove it in, and it worked perfectly. So, it's just good. And normally, when I first built it, I had a little stubby antenna, whip antenna. But you've got to put a tape measure dipole antenna onto it because it just looks cool. Because when it goes in the dispenser, the real ones, obviously, if they're using the tape measure, they just literally wrap around. And when they deploy them, that's it. I mean, you can do a lot of careful mechanical design, but actually you can't beat an antenna that deploys itself. So let me get to the next. So this is during the construction. 3 main printed circuit boards. I don't know why I put 2 images. Oh, that one's just part. Oh, that's one side of it, and that's the other side. Power module. So when I first started doing kind of STEM lectures, it's good fun. You can show pictures like that. But when you've got a built-up cube, people don't really get much of an idea of what's inside. And being from the space industry where we typically build flat sats for software development, I thought, well, we've got to build a flat sat. You do the calculation, although the bus is relatively small because it's only going about 2 or 3 inches down the side of the spacecraft, the frequency is not fast enough that it would worry if you put a ribbon cable that's about 30 centimeters. So I unfurled it, and then you have a payload module. You have the power subsystem, you have the platform electronics. So I started to label it as we would in the space industry to sort of go, actually, CubeSat simulator is exactly how real spacecraft are built. So, and then I started labeling it, going the Arduino Nano that controls the sensors. There's a 3-axis accelerometer and gyro. There's temperature, pressure, humidity. There's the ultrasonics. On that one, there's the laser rangefinder. But we have a payload interface unit, which just happens to be an Arduino Nano, and that just puts the data on a serial connection down to the Raspberry Pi Pi 2.0. That then constructs the message, and as I say, goes straight from the Raspberry Pi, just through a bandpass filter, straight out to the antenna. So there's almost no RF components at all. And the beauty of this is it has 5 modes. So it does APRS. That's the mode it normally boots up in. It does FSK 200 bits per second. It does BPSK 1200 bits per second. It does slow scan TV, and it also does Morse. Actually, I have only tried it on Morse once at the NRC, and Merv, who is the resident Morse expert there, confirmed that it was transmitting Morse. He said it was a bit boring because all he was doing was 1s and 0s, etc. Go on, sorry, John. Dave. I'd heard that was a possibility, so that's quite exciting. Because we have at the NRC we have a dashboard. We have one of the FunCube dashboards, but we very rarely get it up and running. So actually having a simulator that we could get it working. All right, I'm getting distracted. So as I say, labelled it all up, and it's really useful to be able to describe. You've got the plus Z. Plus the y-axis and the z-axis, so you can start to describe exactly as the space industry would do how it aligns and describes where items are. I just found it fantastic as both a hobby project. My son built one, and he's a software engineer, so he's not someone who is terribly used to using a soldering iron. Built it, got it working first time. So. I supplied him the kit of parts, and he supplies the 3D printed. He has a 3D printer, so we have an arrangement. He does my 3D printing, and I give him the kit of parts. It's got very good implementation of the transponder formats, APRS, FSK, BPSK, slow scan TV. I happen to, by sheer chance, capture on the display on a SDR plus the Morse code. So I actually checked that against the APRS packet data. So I mean, I was expecting it to work, but it's always good to confirm. So it's a really nice implementation. It's good to be able to describe and see the different bandwidths of the signals and the encoding. It's got a really neat. This is an FSK. So normally I display it on BPSK because it's just a little bit more of an exciting display. But you could do all sorts of things. So the reason I put it on an angled block is because I'm displaying X and Y accelerometer data, and you can see at the point I turned the rotation up. But actually, if you took that data, you would be able to recalculate back, and you should be able to calculate the angle of the spacecraft. And I think it's just that you can have a simple conversation about it, or with these students that are at a more advanced stage, you can start going, well, actually, let's look at the data, let's match that up with the solar array data, and actually starts to be much more complex. It gets into the maths quite quickly. And so I just find it, it's everything from let's just do a slow scan TV picture all the way through to actually could you use it to calculate something. Do you want to take a slow scan picture? Yeah. Shall we just change it? Change modes is really straightforward. So you've got the green, the blue is transmit. The green is effectively software. It's interesting. That is really interesting. I've just remembered you want to pass it around. We've got a CubeSat version 2. So I've just switched it on. It takes a little bit of time to confirm itself. I'll switch my backup one on. I don't think I've ever had it on quite so long. It's been on since about 10 o'clock. Takes a little bit of time. Yeah, it's definitely running. There we go. So the software is now running. So as I say, it comes up in APRS mode. So if we change it to so I've just changed it into slow scan TV. So it does my call sign when it's just starting up, because we are very compliant with radio amateur regulations. It's also useful because well, it is actually changed. So we'll do it again because it's just gone into. So it's 434.9 megs. Where was my mouse? So I just run up. I should have done this earlier, sorry. So it'll start decoding. There we go. So it's got a standard Raspberry camera. And just for fun, I put the spacecraft next to my Skynet 5 model, took a slow scan TV, which is fundamentally what the US Space Force have just done against the real one. They've just done a rendezvous with the image that I showed you earlier. So I couldn't resist just sticking that in as a slide. It will now. I'm just going to make this more vertical. When it gets to the end, it will. You'll see a red light there. Take a picture. Hopefully, it'll take a reasonably wide angle. Mug shot is probably. There we go. It's sort of got the light, so it's working its way down. You can take one over here as well, so you don't feel left out. And what I did with this one is I built a payload test system because I ran the assembly integration and test, and we'll always build a specific test system. So I just take a feed off the serial link, decode it with an Arduino Mega because I wasn't trying to do something really tiny, and just put it to a display. So it just tells me the raw data that this payload module, and then obviously it's encoded. And if you're looking at the Foxtel M, you can actually verify. It's useful to sort of, if you're again doing a STEM lecture. There we go. Slightly blurry resolution. So on that note, I was really nervous I was going to overrun, so I'm 5 minutes over. So. Thank you very much.
Okay, well, thank you very much indeed, Patrick. That's fantastic. You are forgiven for 5 minutes over. It's almost a tradition of AMSAT, actually, on that side. And for bringing so much kit and showing us so much of what's going on. Really appreciate it, much appreciated. If anybody wants to ask a brief question now, that's fine. We can take those now. Or as Patrick was saying, he's taking his kit downstairs to the SIG area this afternoon. So,
Yeah, thanks very much. I work for the railway, so Stevenage, I used to see it on East Coast Main Line, all the dishes that were there, so if there's anything new there, and you saw my radio mast and my radio hut, if you looked across the station.
Oh, but, right, okay.
Yeah, that was mine. But inter-satellite links, what have we really been doing with that? It's been around a little while, but we've not really been doing very much, have we?
Certainly in military, they've been worrying about that, but also in a high-speed commercial, because if you want to get data from one financial center to another, the fastest, although fiber is pretty good, actually they are believing that if you go to a LEO constellation and you have optical comms between the spacecraft, you will beat the fiber, only by a few microseconds, but in the financial world that's deemed to be of serious interest. So there's a huge interest in optical comms. So a German subsidiary for Airbus called TSAT actually have built optical comm transmitters for spacecraft for probably the last 15 years. And if you look up an ESA mission called EDRS, European Data Relay Service, that's actually using one of the very early optical comms between, and what you're really trying to do is either spacecraft to spacecraft, spacecraft to ground, but now also they're really interested in doing spacecraft to aircraft, and then aircraft to ground, aircraft drones, spacecraft, you name it. You could every company has that diagram where it shows everything interconnected with everything, and most of that will be done with optical, I think, in the future. Yeah. The biggest problem is the standards. The American optical standard is not the same as the European one. And as always, Matt would enjoy this from yesterday's discussion about standards, the different frequency that the Americans and the Europeans use. Don't ask me the frequency.
Hi, Patrick. Thank you very much for a great talk. Obviously, I'm very interested in what you've been talking about. I've also spotted a picture of one of my heroes in the top corner there, of you with what, if I can see it right, Brian May.
Actually, I forgot to talk about this page. So I did bring in some of my only shirts that I'm wearing my Skynet 5 program director shirt, but in the space industry you get a lot of shirts. But my picture that I'm most proud of was at Buckingham Palace, and although my wife has the picture of me talking to the King, I have that one because he is so knowledgeable. Brian is so knowledgeable. We were talking about rovers, and obviously in Stevenage we built the ExoMars rover, and so we were having this conversation about the thermal problem of rovers, and overnight it gets down to about, I forget the number, minus 170 odd degrees C. And right at the end I said, I'm really sorry, Brian, but my wife will kill me if I don't have a selfie with you. Do you mind? And he went, no, not at all. And so we'd actually just had about a 10-minute conversation about Mars rovers going around the moon, and it was fabulous. That was a highlight of my space industry.
The old John wasn't in for Queen because it had more degrees.
Yeah, absolutely.
Okay, unless there's a pressing question now, probably we need to let you guys go and grab some lunch or whatever on that side. But as Patrick has said, he's about this afternoon, so can we show our thanks again to Patrick for a fascinating and I think we're
Thank you. And good afternoon and welcome back to the colloquium. It's my job to give the last lecture. And we're going to end up with an open session if we have an audience. It looks like we may be finishing a little earlier than we expected. I'm presenting this on behalf of the LibreSpace team. And it's specifically about SatNOGS, satellite with no ground station. I'll explain what I mean by that in a second. It's from the LibreSpace Foundation, who were set up to basically to do a lot of things with open source, as Michelle was talking about earlier on today. They're a non-for-profit organisation, and they're founded in 2015, so about 10 years old. I got involved with them in the early days. We did a lot of work with ESA. We got involved with the Genso project as well in the early days for basically a distributed ground system. They say it's 100% space technology. That's the only thing they're interested in. It's either ground stations or building satellites or building software to enable the development of systems. It's 100% open source in the same way that Michelle said with their systems. And it's a little bit about the SatNOGS project itself. As I said, it's been going about 10 years. It's a very small team, but the worldwide population actually involved in SatNOGS is quite considerable. I've done a lot of work with the FunCube and the FunCube Data Warehouse, and we've been a parallel sort of pair of projects, watching each other's activities over the years. It's a network of ground stations. One of the first things they did was actually to design their own ground station. So basically, it was an off-the-shelf, so open source, using commercial components. Basically, a lot of the very, very early days of 3D printing. And they put together their own ground station. That hasn't really taken off. It's been more a case of the software that will actually be distributed for people to use with their own ground stations. They have an open source stack. It's a set of software projects. As I've said, it's a small amount of hardware projects these days. And it's the services that provide the connection between the people's ground stations and the data warehouse, which is similar to the one that FunCube has. The idea was, in the same way that Genso, the Global Educational Network for Satellite Operations, which is what Genso stands for, it was to bring together things like universities, organizations, space agencies, to allow organizations to use the ground stations to watch each other's satellites. The problem is, because of the orbital dynamics, you only ever see your own. If you're a university and you put a CubeSat up, you'd only see it something like 12 times a day. From 2 degrees up to overhead. And basically, you probably only get, of those 12 orbits, you probably only get 6 worthwhile ones. So, and the rest of the time, your ground station remained redundant. So what a good idea if you could actually share that resource with other organizations. The LibreSpace, the Genso project, and the FunCube all use that same model. The system is intended for amateur radio, of course. I'll talk a little bit more about commercial side of it in a second. It's UHF and VHF, L-band, S-band, but it all depends what the ground station provider has. I'll show you what we have at Goonhilly at the end of the presentation, and I've actually set it up to do a bit of capture in the next half an hour or so while I'm speaking. But I think I've set up the system to take about four passes of various satellites. Lots of things in low Earth orbit, as we've seen from the talks this morning. Overhead at any one time, there's probably something like 10 LEO satellites we can pick up with the Libra on UHF. It's not just the amount, it's not just capture. The early days of the Libra system was basically, can we see a signal? That was the basic thing. It's been extended such that the data coming down from the satellite through the ground station into the data warehouse can then be processed, be it SSTV, be it telemetry, or whatever. And because it's open source, the satellite developers can use the Libra system to put a back end on to actually capture the data. It was also intended for STEM outreach, so people can learn about satellite fundamentals. It's nice doing your modelling, but it's also nice to see your own satellite data coming down. The interesting thing that's come out of it in latter days is a launch will carry something like, well, the maximum number of CubeSats ever launched at the same time was 105 about 20 odd years ago. But launches now are becoming more and more common, and the number of vehicles being launched at the same time is in 10s and 20s if it's a multiple pod launch. You have the model of what the rocket's going to do in terms of its Keplerian elements. Some flights are using what's called a free flyer. So once the rocket's gone up, primary payload's gone off, you then launch another vehicle which basically just contains CubeSats or microsats. And they're timed to go off at various points. So you have the basic elements, but you then can't actually work out in this cluster of small satellites which one's which. The Libra system, well, I'll show you an image in a few seconds. We should probably demonstrate with what we can do at Goonhilly. Is you've got you end up with a waterfall of the telemetry of the bandwidth, and in the bandwidth you can actually see Doppler curves, as well as what would be a piece of telemetry you're expecting. In the early days of a launch, you may see multiple Doppler curves, and they can use the Libra system just for the timing of, when would you expect to see the Doppler actually be in the center of that frequency, and they can work out from the timing. They can actually reverse engineer what the Keplerian elements are, and that's been a nice side effect they've come across in the development. They've done a lot of work with the element definition. They take all the information from Celestrack, and it's updated every day. I'll talk about the specifics about a ground station in a second. They provide basically a Raspberry Pi image that you can install as literally put onto your SD card, or they will provide the source code as well, which they can compile up, etc. That piece of software basically talks back to a data warehouse, or they call it in their case they call it the network. I'll demonstrate how that gets used when I get onto the Goonhilly system. But basically, you say, here's my ground station. What are the future passes? And it'll give you the future passes for the next 24 hours. And you select, I want to track that satellite, that satellite, that satellite. But it's the nature of it is you're trying to get the whole of a satellite pass. Because they can possibly have in an hour they can have something like 40 satellites going overhead. So you could, but you end up with an awful lot of overlap between them. So the system's quite capable of saying, I've selected that satellite, what are the next set? And it'll actually work out what that overlap is. Well, you can't have that one. Here's the next one for you. You can determine if you're a satellite builder, you can make the system choose your satellite from the list. Or if you are a research organization and you know there's a cluster of satellites that you want to use, you just tick them off. But the interesting thing is that not only you can use your ground station, other people can use it and schedule passes on your ground station. So, which is quite interesting. The Goonhilly one occasionally sort of pops up and says, "Oh, so I've got about 5 people listening for this satellite. I haven't scheduled that." So it's very much a collaborative thing. There are 280. These slides are probably about 12 months old, I think. So, and the number of ground stations at that point was 287, 163 in testing. There is a difference between the two. The live stations can upload their data to the warehouse and get it processed. Testing ones are basically just operating locally on the Raspberry Pi. As I said, they have a set of ground stations, 287, and the SatNOGS network, which I mentioned. We can schedule. It hasn't come up on that screen, unfortunately. We can schedule individual passes. We can say, given a time span, then in the next 3 hours, what satellites are coming up overhead, and we get a graph basically of all the satellites that are available. You can go click, 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 and choose the ones you want. This is what I was saying about you don't necessarily have to choose your own satellite. You can choose other people's. And if you go silly, you can say, in the next N hours, look at those next 25 satellites I've chosen. What are the availabilities? And the width of the little bars basically indicates how long the overhead pass is going to be. And next slide. Once you've had a pass, it's not very obvious, but I'll point out the information on the screen. Once a pass has happened, the network will store the information that's been uploaded from the ground station. You end up with the waterfall being recorded. If there's any audio available, that's recorded as well. If there's a specific telemetry decoder been written for that satellite, that's available as well. And that's what the little image, you probably can't see them clearly here, but there are a set of images to give you an indication of what the network thinks it's found. It's then down to the individual operator to actually vet those received signals. Let's go on to the next slide. And you can see in the middle the waterfall. I'm hoping you can just about make it out. There's actually a piece of telemetry in amongst that. It's a bit too small for me to see which satellite it was, but on the right-hand side it's actually captured telemetry frames. And if you're the user of that satellite, you can then download them, put them into your processing package, and get the telemetry off. It's also got a database of satellites. So basically, it's got the basic characteristics of what the satellite looks like. its operational characteristics. It's a nice repository for information. We can also get a bit more information about what the type of the satellite is, and what the updated information from Celestrak is. So you always know you're getting up-to-date information. I like pictures. I'm trying to find some more pictures. There we go. We've mentioned that we can do satellite identification through the Dopplers. We've got the decoders available. We've got the dashboards available. So basically, this is the overall picture of what the SatNOGS system is. It's the system as it was when it started out was about 400 ground stations. 10,000 observations per day and demodulated data. In the same way that FunCube has, so the FunCube data warehouse has gone down and up in terms of the number of ground stations available. They have the same thing as well. People become interested, people lose interest. You get a new surge of people coming on board because a particular satellite's been launched, and that's been given more publicity. So the number of people using the system comes and goes. The database has tracked 2,000, probably about 2,400 satellites by now, and over 4,300 different transmitters, be they on VHF, UHF, S-band, L-band, and 2.85 million demodulated frames. So basically where they've actually got something in the waterfall and the demodulators have worked. FunCube is a similar sort of number as well. They've got about, as I've said, the number of decoders they've got is in the region of 100, and they've got lots and lots. They keep the TLE sets for the current TLEs, and they also keep historical ones as well. Using that mechanism I said about the Doppler shift, they've actually managed to identify at least 220 new satellites in orbit. And how to contribute? If you have a Raspberry Pi and you have an RTL dongle, an omnidirectional antenna, you can get onto the SatNOGS network, which is exactly what we have at Goonhilly. Give me a second. And this is what we have at the Goonhilly station. Oops. Why am I not getting any video? Oh, it's on the right. We had the same problem. Oh, there we go. Here he comes, yes. Bear with me a second. You should about see it. This is on one of the huts at Goonhilly. The small turnstile is actually our SatNOGS antenna. You imagine we've got some much larger antennas at Goonhilly. The one behind it is actually the VHF web SDR that's actually that's on the web at it's available to everybody. The SatNOGS system is available. Trouble is, I can't drive it if it's on. I'd have to look at the screen at the same time, unfortunately. But going back to what I said, we can schedule passes. We can then vet what the system has recovered. It's either a waterfall, as I said, or it's a piece of audio, or we've written a decoder ourselves. Some of the SSTV satellites, it will actually decode the ISS. It will actually record the ISS's audio on the VHF, UHF linear FM transponder, and if it's transmitting SSB, it'll actually SSTV. It will decode the SSTV image and actually record it for viewing. It's an interesting little project. I'm running one at home. I probably track about 4 or 5 satellites a day, but as I said, most people just do it for interest. We try and keep this. I try and keep this one fairly active, but it's simply, if you have Raspberry Pi that's going spare, you have an SD card that's going spare. A simple dipole on 2 meters will work equally well. If you've got a turnstile with a preamp, as always, it gets better. The system can drive a rotator using the Hamlib package to call out the G5500. But that's then the commitment of that rotator and antenna has been assigned to the SatNOGS system. It's fun. It's great fun, and it's worthwhile. And that's a quick overview of SatNOGS. Thank you very much. And now I take on the next role. How do I say this? We always are looking for presenters for this colloquium. I take on the role of organising this, and as I said, I've been doing this for 25 years. We look to the audience to send us either a video or a set of slides that we can talk over for you. The more people who actually contribute to this, the better. It is a challenge, and I know the RSGB have exactly the same challenges as well to get people. And with my AMSAT ONSEC hat on, I encourage people to also contribute to Oscar News as well. We're always looking out for more opportunities to put articles into the magazine. This next session was intended to be a question and answer. I'm looking around the audience. I think a lot of the people know most of the questions and answers in any case. If anybody has a topic that they'd like to bring up or discuss, I open the microphone to anybody.
Hello, my name is Andrei. I'm running a very similar network of the stations, and I think we're doing it for 7 years already, plus SatNOGS 10 years. It's quite well, it works. We're getting some data, and a lot of universities interested in what can be the next step? Getting commercials onto it and maybe do some collaboration. Is there any plans? I know there's a activity on the Met raised yesterday about SSDS cooperation, and know that for sure there's a protocol which you can share the data between the stations, right? So currently everything is based on a very old what was the SEEDS protocol mostly. Yeah. I'm pretty sure it's going to be, I know it works, extended to CCSDS and make things more professional. What's the ideas?
The interesting thing about CCSDS, as Matt was pointing out yesterday, they are recommendations. They are not standards. In the old days of computing, IBM were the biggest contributor, and if they wrote a standard, if they wrote something, it became the standard. So if you have a recommendation and you want to write protocol, you might get there first. But yes, I think it's the nature of what SatNOGS did to actually open up the system. With the FunCube, it was not intended to be closed source. It never was closed source, but nobody took it up. It's finding that opening to actually get into commercial or the bigger picture. It is a challenge, yes, and it will probably remain a challenge for quite some time. Any other thoughts, anybody? In that case, I shall put my AMSAT secretary's hat back on again. I had to explain to some people last night why I use the phrase hat, of course, so some of our American colleagues. So, it's my pleasure to say it's been a great couple of days. We've had some wonderful presentations, and my thanks to all the people who have presented, and to the team that have actually put the colloquium together, and to our friends at the BATC who've actually done all the streaming. And I call the AMSAT 2025 Colloquium to a close. Thank you very much.